Hi, I'm DJ Ware. On this episode of the CyberGizmo, we're going to be continuing on with our Linux internals. This time we're going to be talking about interprocess communications. Right after this. Interprocess communications is kind of it's kind of core to everything that Unix, its predecessor from Linux, it did. So you probably don't know that you've used it, but you have. I guarantee you probably have. But what is it? What is it? What do you mean by interprocess communication? What's that all about? Interprocess communication allows a single process to communicate with another. Now, you can also communicate with many to many. So many processes can communicate with many processes as well. So there's two kinds of interprocess communications. There's IPC that occurs between related processes. And we talked about that in process management, that you can have a parent and a child. And if you're not familiar with that, go back and review the video on process management, and that'll explain what the difference is there. I'm not going to redo that today. The second type that you have is one between unrelated processes that are, they're written by different developers. They have nothing to do with one another. You're just taking data from one and passing it to another. And so that's the second kind of IPC that you have. There's a number of mechanisms that IPC uses, and that's going to be really the core of today's talk. There's pipes. There's also first in, first out, or FIFO. There's message queues, there's shared memory, there's semaphores, and there's signals. And that's what we're going to be going through. So let's start with pipes. So the first type of pipe is called an unnamed pipe, and you probably have used this. You probably just didn't realize it was an IPC. But pipes are half duplex, meaning that I can have one process that is writing, one process that is reading, but they can't communicate with each other at the same time unless I create another pipe to do that. So the flow of information is a single direction. It can't go the other way back. So you probably have done this. You probably have used the pipe symbol or the vertical bar. And you take one process and you pipe the output to another. That's an unnamed pipe. And you've been using IPC all along. You probably didn't even know it. But let's just go down and try that. So I'm going to kind of be bouncing around today doing that. So I'm going to take that command right there, and we'll do it from, let's do the R as well, and we'll pipe it to more. So that's a pipe, and of course, there's going to be some permission denied because some of these are unreadable by the user that I'm currently under. So that's all I needed to show. That's it. That's an unnamed pipe. Pretty simple, pretty straightforward. There's also a named pipe. We also call that a FIFO, or first in, first out. Those are also half duplex. In other words, again, it's the process can send out to another one. And they're called first in, first out because the first piece of data out is the first piece of data that the other side reads. Let's take a look at that. Let's go do that one too. And I'm going to need two windows for this, and I think, yes, I have one. So what you need to do first is you have to create an intermediary file. It requires a file in between. So let's do and you do a make FIFO, and then just give it a name. DJ pipe. And then you can do a listing on it. And it'll show you the permissions for that file, and it'll always have a P in the first position of where it always displays the read-write position string. So you know it's a pipe because it has that P in it. So let's I don't know, let's try to echo something to that, and we'll push the data to it. and then I'll use the redirection signal. So instead of writing standard out to my terminal window, I'm pushing standard out to the pipe file, which is what that's, in case you're not familiar with that. So you'll notice that it doesn't come back. It just kind of hangs there. And the reason why it hangs there is because nothing has pulled off the data from that file yet. So Echo is just going to sit here patiently until I get the reader up in order to start reading the data out of the pipe. And then once all the data has been read, then it will go to stop. It'll stop. So let's do a cat on DJ pipe. And you'll see that the Echo program completed, and then I got the message that it sent me right there. Straightforward, pretty simple. Now you can do all this programmatically as well, and generally that is how you would normally use this, is you would use one program to read data from another. So let's go look at another example. So there's shared memory, and shared memory is kind of interesting in that this time it's full duplex. So if I have processes running, they can dedicate a section of memory which is shared between them or between any number of processes. All they have to do is access and request access to that shared memory location, and they all can read and write to it at the same time. It is the most efficient kind of IPC because most of the other ones are going to send syscalls to the kernel for the kernel to do things. But if you're using shared memory, there is no syscall that goes to the kernel. The downside of that is the processes have to be careful and manage that shared memory correctly, and we'll talk about that. So in order to use shared memory, you have to have a program installed. You have to write a program to use it and to write with it. Now, there's a number of programs that already use shared memory in your Linux application box. So, but anyway, the basics is that any number of processes can read or write to the same shared memory segment at the same time. And you can query the shared memory, what's using it, what's in use, by using the IPCS command. So let's go do that. And it not only shows you shared memory segments, but it also shows you message queues and semaphores. And those are all things that are managed by IPC. So you can see everything that's running on the system. So you'll have a key, there's a shared memory ID, who's the owner, the permissions. So in other words, this can't be written by anyone other than the owner Pi. The group permissions are off, the world permissions are off. How much data is allocated to it, and then this is the number of attached processes, and then the status. So there's some other ways you can go in and you can find out what's running in there, but these are allocated already by the system, and these are things that I haven't written. They're just things that are being used right now as we're running. So you can go and kind of query that and see what's going on. So the one problem that you have, however, with shared memory is that you have to be careful with it, because if you have processes that are reading and writing at the same time to that shared location, you may get unintentional results. So the unintentional result would be in the form of a race condition. What is that? What is a race condition? So let's assume that I have two processes that are sharing a memory area. They have a shared memory location that's maybe it's an integer, and process 1 wants to take the initial value, whatever value is there, and it wants to add 2 to it and then write it back. Process 2 wants to read whatever is in the value of that shared memory location, add 3 to it, and then write it back. So both processes, if I don't have any protection at all, both processes will immediately start. They'll read the initial value as 0. Process 1 will add 2, and it'll write back a 2 into that initial value. Process 2 has read the value as 0. So it adds 3 to 0 and it writes 3 back onto the value that's in memory. That's not what we wanted, because what we were wanting these two to do was to count up, right? So that what we were expecting to get here was a 5, and we didn't get it because we allowed both processes to read memory before the other had finished updating. So that requires a mechanism called synchronization, so that when process 1, whichever process grabs it first, it will lock it and it'll block the other process from reading it. And so that other process will just wait until either process 1 or process 2, whichever one grabbed it first, will do its thing, update it, and then it will release it so that the other process can start. And so then, in that case, if you're using synchronization, the correct value would have been 5, and that's what you would have read. And that's a race condition. That's what that is. There's a number of other forms of it as well, but this is probably the most common one. The other thing we have is message queues, and message queues are, now these aren't like there's Rabbit MQ, and there's some from Apache. There's some messaging processes from NiFi which handle queuing, but we're not talking about those. Those are more sophisticated. We're talking about the ones that are actually built into the Linux kernel. And so what happens here is I have a queue, and basically it's a first in, first out queue as well. So it's kind of like, you think of it as a conveyor belt. They have a process that's pushing on a block of data, and it's traveling across to the other process at the other end that's reading it. And it just keeps pushing data on, the other one keeps reading it. So as the process writes data into it, it'll stack up. So if I have something on the front end that's really pushing fast, and it's just pumping data into that queue, it'll just keep making the queue bigger to hold it. Now, the other process on the other end is reading it. And as it reads it, that pops that value off the queue. So that data is gone from the queue. Once the process reads it, that data is gone. And so that's sort of how it empties the queue and gets it to flush out. But the downside is that this is managed by the kernel. And in order for that message queue to work, there has to be a syscall that's done every time there's an interaction with it. And so there is some overhead involved, because you're saying stop, do this, come back, then stop, then do this, then come, and so that goes on and on. So, but message queues do help eliminate the race condition, because I can change. I am not modifying values inside of a shared memory location. I'm just sending. So if I'm adding, let's say I'm adding 2 to a number, then I'm just passing that down to the other process. And it's going to, let's say if I add 2, and then I add 3, and then I add 4, it's going to see all the 2, they add 2, they add 3, they add 4 as it comes down the line. So the message queues can also be a little bit more complicated, in that you can have a single process that's writing data out to the message queue, and you can have a whole bunch of other processes that are reading it and processing it. That would be concurrent. That would be adding some concurrency to the system. Say that maybe your process on the reader side is slower, it's doing some other stuff, and the process 1 can really send in data a lot faster, and you want to scale up your output so that your performance is about the same. You can do this. You can have multiple processes reading it. You can also have multiple processes writing into it as well. I mean, that's not a problem either. But in this example, I just wanted to keep things simple. So let's say that process 1 writes an A and a D and an F, and that gets stacked onto the queue. Well, I don't know what these other messages are in there. There might be more. But process 2 comes along, it does a read, it pulls A off. Process 3 comes along, it reads the next message in the queue because A is now gone. And so it reads D, and then that's gone. And then so process 4 comes along, and it reads the next value, which is F. And then that's gone. But you'll notice that process 2 didn't get to see all the data. Process 3 didn't get to see all the data. Process 4 didn't get to see all the data. It only got to see what was left on the queue and what was next on the queue. So yeah, data remains in that queue until it's read, and once it's read, it's gone. Semaphores. Semaphores are kind of an interesting construct. This also requires a program to use it. I'm not going to delve into that here today. I'm just going to describe what this is. So semaphores are used to protect critical common regions of memory that are shared between multiple processes. You can think of semaphores as they are definitely part of the operating system. They are, in fact, not only part of the operating system, they are the most atomic piece, that is the lowest level of the operating system, because what they do is, as data is being, and let's say programs are being loaded and data is being loaded, and then it's being torn down again once the program leaves, semaphores is what is used to protect that region of memory from being overwritten by something else. And so there's two kinds of semaphores. There's a binary semaphore where you have only two states, a true and a false, a 1 or a 0, an available or unavailable, a locked or unlocked. I mean, that it's just those that are just binary states. So, and that's the most common use in the operating system that you'll find. There's also counting semaphores, and that's also used when it's tallying up the number of processes or the number of pages or the number of data blocks that are being loaded. But that allows arbitrary counters for resources that you might have. And both of them are definitely used in the OS. So, okay, that's great, but how does this thing work? So when, let's say a process is running along and it wants to allocate access to the semaphore. So maybe the semaphore is blocking some specific region of memory or some resource on disk, or maybe a network instance that's going on. But the process wants to get access to it, and so it checks the semaphore to see if it's available. And so it attempts to allocate that semaphore, and if it's available, the kernel, the Linux kernel, will block any other process from getting to allocating that semaphore until that first process is done. So it's like a lock on that whatever region of memory that particular or whatever thing it's protecting. So it'll issue, and then the process as it runs, process one as it runs, it'll reach a completion state, and then it'll release the semaphore, and the kernel will then unblock the other processes that are waiting for it. And then it'll make them available, and the other processes will then continue on. But it's too bad that, operating system course, I took the last one. I mean, the last course in operating systems design was offered, I think, at least by one of the schools that I was going to at the time. I think it was around 84, 85, somewhere around in there. And I wanted to continue on into that, and my advisor said, you're not going to go anywhere with that because everybody knows everything there is to know about operating system design. Boy, are they wrong. Anyway, that's my opinion, and that's one of the reasons why there haven't been any new operating systems to challenge the big three since. The last major operating system that was really developed was probably Herd, or it would have been, at least in the Linux world, or it would have been the next OS. And there haven't been any challengers since then to Windows and Mac OS and Linux since then. I mean, I'm counting Linux has already been established in around 92 or so, but yeah, and it's a shame because there's so many things that Linux just doesn't do right. And there's so many things that it could be, there's so many things that could be done to improve it. So at least from a core level, it's kind of old-fashioned in some of the things that it does. The last one is signals. Signals are used as a notification of some event that's occurred. And those are used in the form of a trap or a software interrupt that just out of the blue will send an event notification to your process. And so if you do, let's go back to this again. Just get this cleared off. If you do a kill -L, you can see all of the signals that are implemented in your particular version of the kernel. And you'll see things like number 2, SIGINT. SIGINT. That means that there is a control C that was sent to your process, and that will generate an interrupt that your process can either handle it, or it can let it clean up whatever it has to do to clean up and then shut down. There's also ones that are crash out, and crash out ones are not. You're not given, and in the process, you're not given the opportunity to handle them. You can't block them. You can't step in and say, "Oh, I'm just going to do this, and then I'll get back to you." Like the SIG9, the SIG kill command, you can't block that. The kernel will immediately terminate your process. It doesn't even let you handle it. Now, user 1, and there's some other user, like a user 2, those you can. SegV you can't block. That's a segment fault. And the SIG pipe means that the pipe has been broken. That generally will cause. Now, you probably have seen that. So if you're writing a whole bunch of data, let's say you have that pipe command open. I should have showed you that. But if you have that pipe open and you're just sending a whole bunch of data through there, and you start the reader up and it starts to read the data off, maybe you have a sleep, like a 1-second sleep in the middle. So it's writing a line, sleeping for a second, writing a line, sleeping for a second. And the receiving process, you do a control C to, that breaks the pipe. And so the front reader will break and it'll shut down. So yeah, you can't block that. SIG term, that's a terminate. You can't block that one either. So those are called crash outs. And yeah, those are called crash outs, and you can't stop those, no matter what you do in your program. So some final thoughts and wrap up for today. Many of the IPC, or the interprocess communication constructs we use today, came to Linux from Unix System 5. Now, a lot of those things, they're not in their original form as they came from System 5. The POSIX has standardized the IPC, with good reason. I mean, if you're writing a program, let's say on BSD that's POSIX, you want those same constructs to work the same, so that you have some portability between different flavors, even of Linux, so that you don't have someone writing an IPC construct that isn't understood. Let's say a Red Hat construct isn't understood under Ubuntu, or vice versa. You would not want that. So there's POSIX standards that have governed those uses and also have extended them. For example, POSIX has implemented standards to handle threads, which weren't, of course, in the original Unix System 5 spec. And there's a lot of other features that have been added as well. So the ones that I showed you today are all POSIX, and they were all available in Unix System 5 as well. So they were just different. Some of the structures were different, but POSIX has definitely improved things, I think. So that's all I had for today. What I think I'd like to do next time is talk about the virtual file system. If you guys are still interested in continuing on with this series, I just have 2 more things to do, and that's virtual file system and networking. So I'll touch on one of the major things besides IPC. The virtual file systems are really the major component of Linux, because everything in Linux and Unix is a file. So it's all based around that premise. So I hope you enjoyed this video, and if you did, please like and subscribe. And as always, hope to see you again next time, and bye for now.